Okay, the webinar is being started.
Recording in progress.
I now also have a monitor here where I can see what participants can currently see.
Perfect. So I guess I wait 1 or 2 minutes and then we can start on time. All right, so I guess it's 5 o'clock, so let's get started. It's my great pleasure to welcome you all to the Artificial Intelligence Colloquium at RWTH Aachen. My name is Sebastian Trimpe and I am leading the chair for Data Science and Mechanical Engineering. And it's my great pleasure to welcome you all today on behalf of the RWTH Center for Artificial Intelligence to our very first edition of the new AI colloquium, or in short AIC. So before we start our colloquium, let me give you a brief introduction and say just a few words about about this new series of events. So we've started this AI colloquium, or we start this AI colloquium today, and the goal of this colloquium is that roughly every 6 weeks we'll have a renowned scientist, either from our university, from RWTH, or from other universities, to present state-of-the-art research methods and applications of AI. And even though we start with a slightly different frequency of talks, so in steady state, the goal is to have a talk roughly every 6 weeks, and we'll be always on Thursdays from 5 to 6 p.m. If you haven't visited our website, here's the link as well as the QR code, and you will also find us on LinkedIn, Twitter, and YouTube. And we are very happy that today we have as our first speaker our colleague Bastian Leibe, and then as you can see here on the list, we already have 2 more talks scheduled already, Zeynep Akata and Wolfram Burgard after the holiday break. This colloquium is organized by the RWTH Center for Artificial Intelligence, and roughly a year ago, a bit more than a year ago, we started our activities in the RWTH AI Center. In the board of directors, we have Bastian Leibe, Gerhard Lakemeyer, Will van der Aalst, and myself. And the goal of the AI Center is that we want to strengthen and focus the AI research at RWTH. And there's if you've been following the AI Center, we had a couple of things happening throughout the first year. So we created a website which is there to represent the AI activities that we have at RWTH, and we are always expanding the website with more activities. We are involved in a couple of grants, both for research and education. Some of these we are coordinating from the center, and we also have launched several events. Hopefully some of you have noticed that we had the AI week earlier this year, which had actually several events, both for the general public, also scientific events. And one of the events there was a scientific colloquium. And we thought that we wanted to continue this series, and this led to us introducing this new series, or the new colloquium on AI that we're starting today. And the main persons behind the organization of this colloquium are actually Marco Pegoraro, as well as Hannah Markgraf, who are also both here today, and you will see them. You should see them among the panelists. So thanks, Marco and Hannah, for the organization. So with this, we can actually get to today's event. And before I will introduce Bastian Leibe to you, let me just say a few words on how we organize this colloquium today. So this talk will be recorded because we intend to make it available also afterwards on YouTube. The Q&A session will not be recorded. So if you have a question, please feel free to use the Q&A chat to ask the question. And then after the talk, we will have the Q&A session. All right, so this now finally brings me to introduce today's speaker. And it's my great pleasure to introduce our colleague, Bastian Leibe, to you. So Bastian is a full professor at RWTH and leads the computer vision group. Bastian has received the diploma degree in computer science from the University of Stuttgart, as well as a Master of Science degree from Georgia Institute of Technology and the PhD from ETH Zurich. And Bastian's research interests are in particular in computer vision and machine learning, in particular also for dynamic visual scene understanding, which we'll hear more about today. Bastian has received a number of awards, and I won't be able to tell them all, but maybe some of the most notable are CVPR Best Paper Award in 2027, the AGM Olympus Prize, and as well as the UV Elvata Award. And Bastian has also received actually 2 ERC grants, the ERC Starting Grant and the ERC Consolidator Grant. And last not least, Bastian is also currently the spokesperson of the RWTH AI Center, but today Bastian is not here primarily in that role, but he's here today as an internationally leading researcher in computer vision, and that's what we'll hear about more in your talk. So Bastian, very much looking forward to your presentation, and I'll hand over the virtual floor to you.
Let me unmute. Okay, so thank you very much for this kind of introduction. And hello and welcome everybody. Today I want to shed a little bit of light on some current research directions in computer vision, progress that has been made over the last years, and some current trends. In general, in computer vision, if you look at the field, there has been a huge amount of progress, and deep learning has really been a driving factor behind this. So today I want to illustrate some of that progress using examples from our work. Note well, this is not the only progress, of course, that there is a lot of progress in the entire field. It's just those areas where I have illustrative examples that I can show this on. And of course, here also, this is not only my own work. This is in particular work by my PhD students from my group. So here, over the course of this talk, I will present work from a number of students, Paul Vogtländer, Ali Attar, Jonas Schuld, Istvan Sarandi, and many more who contributed to this. But let's go into the details, and here the overall goal that we're trying to address in our work is dynamic visual scene understanding. So that is, we are interested in the problem of observing video of the outside world and then trying to make sense of it. And one common application that we are looking towards is the kind of visual understanding that you need in order to navigate crowded scenarios. So suppose you're walking over a busy town square, for example, here in Aachen, and you can see the image is already a number of years old. Nobody is wearing some mouth protection. But essentially, what you see here are very dynamic scenes. People are moving in all different directions. Some of them are walking independently. Some of them are forming groups. Some of them are engaged in conversations. They are carrying different kinds of items. Sometimes those items, like heavy shopping bags, can influence the motion dynamics. And in general, they are interacting with their environment. They want to, for example, go to a shopping stall, buy some groceries, and then afterwards turn around and continue on their tours. And so if we now want to safely navigate through such a scenario as a mobile robot, as some future autonomous vehicle in slightly less crowded scenarios, then our goal becomes to understand what is going on and to make predictions. How will the motion continue in such a scene? And this is a very challenging task for machines, but it's a task that we humans can routinely solve. So since all of our motion, all of our human navigation is based on those kinds of visual capabilities, in order to really develop mobile applications like self-driving cars, service robots, but also assistive devices like autonomous wheelchairs, we really need to get to a similar level of visual scene understanding in order to enable those applications to take place in a world shared with humans. Now, as I said, in the field of computer vision, there has been a lot of progress over the last years. So applications that you can see here, for example, are first attempts at autonomous driving. And really a huge effect in all of that was the development over the last years of a number of very basic vision components that nowadays have been brought to a level that works very well. So here, one such basic component is object detection. Detection of traffic participants, cars, pedestrians, people. Nowadays, we can do this very robustly. And then the next step is to also track objects, estimate temporal coherence, estimate the motion, not only in the images, but also in the 3D space. And here, based on a limited number of categories and certain scene constraints, this can already be done quite robustly. What we also see as another task that is gaining more and more traction is semantic segmentation. So here, this task denotes the question, what would be the category that every pixel shows in an image? So we want to get to a pixel accurate representation here. And if you look at the results of recent methods, this is an approach already several years old, you can see that current methods, mainly driven by deep learning, are already getting to impressive levels of detail here. We can really get almost pixel accurate boundaries for objects such as cars, pedestrians, bicyclists. We can even segment people riding on a motorbike or on a bicycle and get that kind of interpretation. So that's already a good indicator of what will soon become also available as a sensor, for example, for use in cars. But now, looking at this research progress, I want to highlight a number of directions that have gained a lot of traction over the last few years. And in particular, I've mentioned that a lot of progress has been in deep learning. And one thing that you're in many cases already familiar with is how does deep learning look at a level of the lecture. So simple convolutional neural networks, multiple convolution layers, pooling layers, classification. This is pretty much what is taught in the classes, but I want to show you also how those kinds of approaches can now be applied to more complex kinds of data or more complex tasks. So for this, I will highlight 3 directions in computer vision. The first such direction is to move towards pixel level tracking. After that, we will look at more detailed human motion analysis, and then we will look at 3D scene understanding, where the input data is 3D data in the form of point clouds or meshes. So let's look at the move towards pixel level tracking. I've already shown you that object detectors have become very powerful, and typically when we see older results, they're all represented as bounding boxes. But as you've seen from the video before, segmentation now becomes more and more accurate, and we can really move now towards representations that try to represent objects at a pixel accurate level. And this is a trend that has been going on now for a few years. And it really leads to a much increased level of precision. Where before we just had rough bounding boxes as annotations and as the data to work with, now more accurate appearance models become possible, and this again leads to the possibility for more accurate detailed analysis of the results. So here in particular, there are different directions, different subtasks that the community has focused on. One subtask is video object segmentation. So here, the basic setup is you're given one frame of a video with segmented objects, and your focus is to then consistently track this object motion over time over the entire video sequence. Another such task is video instance segmentation. Here, you're not given any initialization by a human user, but you're focusing on a number of known object classes, such as, here in this case, elephants, cars, people. And your goal is to, again, create a temporally consistent segmentation for every object with automatic initialization. And there's a third related task that we call multi-object segmentation and tracking, where you try to put all of those components together and to really develop tracking approaches that work at the pixel level. Now, in my group, we have worked in all of those three directions, and in order to enable progress here in especially multi-object tracking and segmentation, one activity we have been focusing on for several years now was to publish data sets, annotations for existing data sets that really enable researchers to perform these kinds of tracking tasks at the pixel level and to get consistent evaluations for that. So that was work by my PhD student, Paul Vogtländer, and several of his colleagues. Now, if you look at how current approaches for this video segmentation work, then you have two basic classes of approaches. The first class of approaches starts from a given ground truth initialization, so some mask given for one frame. And then these approaches focus on tracking those masks over time. So propagating the mask from one frame to the next. And this could be supported by additional cues like optical flow. And then you try to evolve those masks over time. The other main direction are what we call proposal tracking by detection approaches, where you start in each frame anew by trying to solve a recognition problem. And this is done typically using a region proposal network that proposes a set of possible regions. And now for those regions, we can perform some refinement and we can try to group them and associate them over time in order to get temporal tracks. Now, in both of those directions, there has been a lot of progress that has been made. So here for mask propagation, this was dominant in the early times of video object segmentation. So here, starting at around 2017, first deep learning approaches and benchmarks came out. And then over the years, a number of state-of-the-art approaches have been published that have pushed performance to new heights. And here, over the last years, we were very active also in this field and had several contributions in this direction. I want to highlight here in particular one issue with those mask propagation approaches, and that is they are trying to build up effectively a classifier that tells apart the pixels of the object from the background. And this classifier is propagated over time. Now, the first approaches that were published here performed some fine-tuning to adapt that classifier in the first frame. And that turned out to be very slow because you needed to solve a learning problem before you could then perform propagation on the video. So for a long time, therefore, approaches towards this have been divided into two classes: approaches, algorithms that were fast, or algorithms that were accurate. And only in the last few years, now representations have been proposed that work around this problem by not training a new classifier, but by propagating embeddings. And you will see this as a common theme throughout this talk. We are looking at embeddings basically as an intermediate learned representation that is used then for different purposes, mainly for keeping object information over time and for matching that. Now, here I want to quickly highlight one approach in this temporal progression, BREMVOS, that my group worked on. So here, this serves to highlight the different steps in this kind of pipeline. So the first step in those approaches here is a proposal generation stage, where we take an image and we have a proposal network that generates possible regions that we might be interested in. So this network learns a lot about what constitutes an object, and it makes some proposals. They could be potentially overlapping. They might not be perfect. So in the next step in this BREMVOS approach, we perform a refinement step in order to refine those proposal regions to give us segmentations that better align with the knowledge of known classes. Then those proposals are then associated over time and merged into tracks. And for this merging step, we need to compute appearance descriptors. And in order to do this, we can use some specific network structures that learn a score that allows us to tell how similar two regions in different frames are. This is what we call a re-ID score, but we can also use this mask propagation idea in order to propagate the mask over time and use optical flow in order to find already a candidate region where the mask would be. Now, this BREMVOS approach, I highlight it because historically it was very successful at the time of its publication, 2018. It was the leading approach. It won a number of benchmark challenges, but the field has progressed so far that by now it is still among the good methods, but there are many methods that have nowadays been proposed that outperform that perform better. So here, just some visual results. This is the kind of results that we can obtain with such an approach. So we can achieve tracking even if we have viewpoint changes for objects, but a limitation is, since this only cares about propagating masks, not really about understanding the underlying structure. When objects are occluding each other, we still have problems, and we get switches, identity switches between those methods. Now, here, this was an example for a proposal tracking by detection approach that also used some mask propagation scheme. In the following, I want to quickly highlight another way how this problem can be approached, but this time using a different paradigm. So in particular, we wanted to develop an approach that does not rely on a first frame mask, so that it can be applied without human initialization. And we also wanted to avoid this two-step tracking by detection approach. And instead, we wanted to ask the question, can we take advantage of the spatio-temporal progression in video in order to find out what objects, what are consistent object tracks by formulating object as a grouping problem, object tracking as a grouping problem. So here for this, we are trying to find a way to associate pixels jointly across space and time and to develop the appropriate representations for this. So for this, The main idea is that we want to model a video clip as a single 3D spatiotemporal volume. For each pixel, we want to learn an embedding. So this is, again, just a fancy word for an internal learned representation that encodes the essential properties of that pixel. And we want to do this in a way such that embeddings that belong to the same object instance form a tight cluster. And then we can use a clustering process in order to automatically group all pixels that belong to the trajectory of the same object. Now, in order to make this work, we need to work on the embedding formulation. So we need to find a way to encode the learned representation that it supports this task. And here in our work, what we did now was we took as input a spatiotemporal volume, so a short snippet of the video clip. Then we have a network with an encoder and a decoder structure. So the encoder creates those embeddings, and then the decoder uses the embeddings in order to generate the output. And here we want to generate 3 different kinds of representations. We want to get the embeddings themselves that are used to encode the pixels. But we also want to perform a grouping process. So we want to get clusters with a cluster center, so a center of the object in image coordinates, and also a center of this trajectory in our spatiotemporal volume. And we want to also learn the variances of those clusters to find out how many pixels should we assign to those. So the way how this is done is by now designing the network structure such that we perform a voting in our embedding space. We generate embeddings that should be grouped together if they belong to the same object. So here, at that point, we use supervision from a set of training sequence to achieve the effect that we get tight clusters. And in once basically this embedding space here will then be used as the starting point for initializing a grouping process. The challenge with this grouping process is, again, how do we formulate this clustering problem in a framework that is now compatible with this deep learning pipeline so that we can, again, perform end-to-end learning. And the idea behind this step, when we want to use the network for inference, is that we perform the grouping step in a series of steps. In the first step, we try to find seed points for the objects. So we try to infer a heat map for the center position of object candidates across the frames. So here you see the spatiotemporal volume. Here the horse is jumping over this fence. And what we now want to get is, for every frame, a heat map that contains pixels on the object, and it should have a peak at the center of the object. So we want to now extract peaks in those heat maps as possible seeds in order to start a clustering process that would then perform the spatiotemporal association. And at those peaks, we now use the regressed values, the estimated values. What would be the covariance, so the basically the width of the cluster at those points. So this is, again, our network predicts the means and it predicts the variances. So we can simply use our estimated variance outputs at those points. And this gives us then directly a set of hypotheses for cluster centers. and we can look up the mean values. We can look up the variances for the clusters from our output space. This gives us hypotheses for the clusters and for the points that we should group together with those. And we can do this for each of the extracted clusters, and then use those cluster identities in order to group the corresponding points. Now, I described the inference process, but this inference process is important also during learning, because now this tells us which of the points would be associated to the same object. And in the learning phase, this would then directly give us the information which pixels we should supervise. So for which pixels we need to apply a loss to change the representations so that those pixels also get better grouped in the next learning iteration. Now, as I said, we use an encoder and decoder, and here I just wanted to show you a visualization. Again, a lot of work has been done here in the computer vision field, and the types of network architectures that we now have available are much more powerful than the initial convolutional networks. So basically, what such an encoder typically looks like is a multi-scale representation, so with multiple pooling stages and then multiple unpooling stages, so that we effectively get a feature pyramid network with features at multiple scales, and that gives us outputs at the different scales that we can then use for different scale representations of the input data. The decoder then performs a series of iterations. Here we use a so-called temporal squeeze excite network. It performs a series of squeezing steps where essentially the information that is pushed through a bottleneck and then decoded again and pushed to a bottleneck and decoded again. So after those multiple squeeze steps, the information is refined so that we the network learns to focus on the essential features. And we start doing this at the lowest resolution, then we upsample, have another such series of squeeze excite layers at the next highest resolution, and we do this multiple times until we arrive back at almost the original resolution. So now, here are some qualitative results that you can now see in this process. And what is interesting is to observe here a visualization of the embedding space. So basically here you see the heat maps that are predicted from each frame, and in particular the different object identities that are automatically extracted through the clustering process. So, and as you see, over time, those heat maps evolve, but they form a trajectory in this 3D volume so that our grouping process is able to associate the corresponding pixels over time, and this way solve tracking as a grouping problem. The same basic method is also applicable to driving scenarios. So here we have longer sequences, and as you can see, the clusters are much more focused on those static cars because their appearance changes much less. And again, you can see we can use this approach also to get pixel level tracking results for those kinds of scenarios. So overall, we've evaluated this approach. We called it STEMSEC for spatial temporal embeddings for video segmentation, and we've applied it to multiple benchmarks and can confirm that it achieves state-of-the-art results on several current benchmarks. So at least at the time of publication 2 years ago, this was state of the art. But this shows you one possible, one direction, one trend in the computer vision domain, namely to use those kinds of embedding representations in order to track the progress of object appearance over time. Now, in the next part, I want to focus on a different problem, namely detailed human motion analysis, where now our goal is to analyze a person's motion over time. And in particular, we're interested in the 3D motion. So we want to get the 3D body poses as a skeleton that we can really interpret in 3D and place in a 3D world coordinate system for interpreting the detailed actions and interactions that people take. Now, the approach I'm going to present here is called METRO, metric scale truncation robust heat map estimation for human body pose estimation. And there is an extension that we call METRAPS that does this also for absolute 3D position and scale estimation. Now, the particular approach is remarkable because it's extremely simple. So over time, more and more complicated architectures have been proposed, but essentially here, the network that we're using uses a fully convolutional backbone. And this is really just a standard network. You can use a ResNet 50. We used also different kinds of networks in the process. And then we generate a volumetric representation from that, where we are again generating heat maps. So heat maps for the different body joints. So for every joint in a skeleton representation of the body, we want to estimate its position in 3D. We generate a heat map from that, and we extract the maxima in this heat map as locations, possible locations for this joint. Now, when you do this, the one challenge is how to actually train the network. We want to estimate 3D positions, but there is relatively little data available that has 3D skeleton annotations. So what we did was we used one pathway to train our network on the available 3D data. But in addition, we also took a projection of our estimated 3D body pose into image coordinates, and then we evaluated that with data that was just annotated on image positions. So joint locations in image coordinates, for which much more data is available. Now, when we do this, we need to solve a scaling and shifting alignment problem, because in this transition from 3D to 2D, the camera transformation is not always given. It's not usually available. So what we did here was we designed the network in a specific way so that we can estimate also the camera transformation from data, and that allows us to find, first of all, a 3D location for the joints in a metric space, and to also better handle the scale and shift alignment problem. Now, this approach is very easily applicable to robotics applications. So here are some results from a recent European project on robotics, where the goal was to develop such detailed human person tracking capabilities on board of a mobile robot that wants to navigate through a crowded scene. And in particular, one thing that you can see that is the distinct advantage of our method is that we're able to also get very good estimates for those body joints that are outside the image, which is particularly important for a robot that drives very close to people, where the feet are not really visible in the video data. So here are some more results also for multiple people. What you see always are the estimated 2D body joint positions in image coordinates, and then the resulting 3D joints. So here we've performed work in multiple directions. One direction focused on getting those kinds of results optimized for processing, ideally in real time on embedded GPU devices, and the other direction on making this more scalable and getting basically models that can work also on any kind of YouTube videos that you would like to apply it on. And here very recently, Istvan, the PhD student who has worked on this, has made a software release on GitHub, where this kind of approach now is available. You can download the model, you can apply it to any kind of videos that you've maybe recorded yourself, and what you get out then is the tracked body joints in 3D coordinates. We have some nice visualization tool that allows you to then also watch the 3D trajectory over time. So here there is a video available on our YouTube page. For some reason, it didn't work here, embedding it in this presentation. It did, it worked. So sorry, I just needed to wait for the click. So here, what you can see now is the accuracy level that we can obtain. And remember, this is just monocular data. So everything that you see about the 3D nature of the scene has just been learned by this very powerful deep learning model. So here, in particular, one application that we foresee for this is to look at interactions of people, sports analysis, and here we want to look also into how well this kind of results transfer to other scenarios where this kind of 3D motion analysis can then serve as an input for all different kinds of downstream tasks. What we're also looking at is how to combine multiple of those estimation directions. So in particular, can we build up networks that can estimate body part segmentation, 3D or 2D body pose estimation, attribute recognition, and a number of other visual analysis tasks in an efficient way in a single network, so that it can be applied then really to drive a vision system for a mobile robot and to make it safer to drive through very busy scenarios. Now, in the final few minutes, I want to highlight a third trend, and that is something that is very different from what I've shown so far. Up to now, our input were always images or videos. Now, in the next work I want to present, our input is 3D data. So, in particular, what we look at here is point cloud data that has been, for example, scanned by a 3D laser scanner or obtained using stereo data, and that gives us now an accurate 3D reconstruction of rooms or entire office floors. And now what we want to do is to obtain a semantic segmentation, but now at a 3D point level, where we want to know the class of each 3D point, and in an extended problem setting where we talk about instance segmentation, we also want to know which of those points form individual chairs or individual desks. Now, one basic problem when using this kind of data is that we need to find representations that we can apply deep learning to. And here, over the last years, a number of different representations have been used. So one direction focused on voxelized data, which is very, very easily admittable to convolutional networks, because we can then think of convolutions as an operation in this 3D space. There were some developments necessary for that to make it efficient enough, but nowadays this voxelized representation is probably the most prominent one. In this representation, however, in this paper, we wanted to look at something different. Namely, we wanted to look at point cloud representations, and we wanted to look at mesh representations. And in particular, we wanted to combine their advantages and use both of those in order to get more detailed level of analysis for what the point cloud contains. Now, in order to highlight why it is beneficial to look at both point cloud data and mesh data, we want to focus on the question, how do you actually define neighborhoods? Because we need to define a neighborhood in our space in order to perform something that we can map as a convolution. And there are two different ways that we use neighborhoods here in this work. One is we can define Euclidean neighborhoods, which are defined in Euclidean space. So basically they are based on proximity. We can represent a neighborhood either using a k-nearest neighbor scheme with a certain fixed number of neighbors that would define a certain radius of a neighborhood, or we can define a radius and then take all the points that fall inside this radius. On the other hand, we can also define geodesic neighborhoods. Geodesic neighborhoods are neighborhoods that are defined on the mesh surface. And if you compare the distinct properties, then a Euclidean neighborhood can be beneficial if we want to express interaction between different disconnected parts of objects, whereas a geodesic neighborhood is beneficial if you want to capture the object shape along the surface. Now here, in the work I want to present you here, we wanted to combine those two types of information into a common network. And the basic architecture, again, follows an encoder-decoder scheme. So this encoder-decoder scheme is very, very popular in computer vision in general. And it basically boils down to a sequence of convolution operations to compute feature representation, then pooling to reduce the resolution, again, a number of convolutions, pooling until we get at a low resolution version. And then there are a set of unpooling operations to get back to the higher resolution. This way, we are creating a bottleneck representation here where we are forced to encode the essential properties of the semantics in the vicinity of a certain point, so that from the bottleneck, we can then reconstruct the output again. Now, when you do this, the basic question is, how do you define convolutions? And in particular, here we used a special form. We introduced a so-called dual convolution module that performs convolutions in both the Euclidean neighborhood and the geodesic neighborhood simultaneously. Then the second question is, how do you solve the problem of reducing the resolution? It's easy to perform a pooling operation on a point cloud, but that kind of point cloud reduction would not leave us with meshes that we could consistently then represent at different resolutions. On the other hand, there are mesh simplification approaches, but in those we remap the points, and therefore we lose information about the 3D Euclidean neighborhood that we would need in order to define Euclidean convolutions. So our solution to that was two new modules that we introduced. First, the dual convolution module that performs a Euclidean convolution in the Euclidean neighborhood, and simultaneously a geodesic convolution along the mesh surface. The results of those are concatenated and then processed again by the subsequent stage. In addition, we introduced a pooling and unpooling mechanism that uses a mesh reduction method in order to generate a lower dimensional representation for the input mesh, where we perform pooling operations, so multiple mesh vertices are reduced to a single vertex. And then again, we have an unpooling operation that tries to undo this. But of course, the problem is in the unpooling, if we have low resolution mesh, it's not obvious how we get back to the high resolution mesh. So in order to enable that, we save a pooling trace map that gives us the information which vertices were collapsed onto a single vertex in the pooling stage, so that we can then later on undo this step. In particular, here we experimented with two different mesh simplification algorithms from the computer graphics literature. So here vertex clustering and quadratic error metrics. And in the paper, we compared them in detail for this purpose of semantic segmentation. But essentially, we showed that this kind of architecture, when taking the right design decision, works, and that it also has a distinct advantage above just using either Euclidean or just the geodesic convolutions on their own. So here you can see some results. I've already shown you 3D results at the very beginning of this part, but now here, just as a visualization, this would be the input scene that you're presented with. This is the ground truth that we're hoping to obtain. And this is the level of quality that the dual convolution meshnet can provide. So you can see that for large parts of the scene, we perform the correct classification. So here there's an error map that highlights those regions which differ from the ground truth. And you can see that for large parts of the scene, this works pretty reliably. We have some error sources around here, the precise borders of the store, and some other 3D ambiguities of structure. In the bottom example, you see an interesting case where in the ground truth, this armchair is labeled as a sofa, whereas in our estimated results, it's labeled as a chair. And sometimes that matches the annotation, sometimes it doesn't. Also, you see some effects that are difficult to annotate. Like here, there is a painting on the wall, and in the ground truth, it's labeled as wall, whereas here it's labeled as something different. We don't have a class for paintings in this data set. So then it was confused with a window, which is incorrect in that case. But you can see those errors that are obtained at that level are still very much understandable. So here, again, in this entire field, a lot of progress has been made. And that means that those kinds of methods also now become interesting for applications. So in conclusion, summarizing what I've said in those different directions, I've showed you some trends, some directions in vision. This is not far from being complete. There are many very exciting things going on. But the reason why all of that is so exciting is that things are really starting to work. And in particular, you can now see vision methods being applied in mobile robotics, in mobility applications, in all different kinds of applications, smart cities and other domains. This has become possible because we are getting increasingly accurate image representations. Part of that is due to the focus of moving now from coarse representations to pixel level representations. But in general, for many such limited tasks, the output quality of current computer vision methods is already sufficient to enable some practical applications. This does not mean that the problem is solved. No, it's far from solved. What becomes apparent, in particular, when you look at those applications, is that there are major issues still when you want to bring really vision to the streets. And that is that the typical benchmarks that vision methods are trained on only capture a small portion of the variety of real-world data. And in order to make vision methods work on the data, or general deep learning methods work on the data, a lot of work has been invested in supervised learning. So that required very expensive human level supervision. And in order to really make approaches more scalable, one of the main problems of the next few years will be how to reduce this level of human supervision so that we can get towards weakly supervised or self-supervised methods that can achieve similar results with much less training data. The main objective of many of those directions is to arrive at a level where we can make predictions about how the future scene will continue to evolve over time. And that is also a main challenge now that people, many groups are focusing on, and where also I expect that over the next years we will see continuing exciting progress. And in addition, we are seeing how deep learning methods are being applied for many different types of data. So where really, since this spreads out to all different fields, also the number of researchers working on this multiplies and the progress further accelerates. So with that very positive outlook, I want to conclude my presentation. Thank you very much for your attention, and I'll be happy to take your questions.